Imagine you are listening to a faint whisper in a noisy room, trying to pick out crucial words from the surrounding chatter. In neural signal analysis, we face a similar challenge, distinguishing meaningful brain activity from background noise and unwanted electrical interference. Setting the right boundary is absolutely key. So, how do you set an effective amplitude threshold? An effective amplitude threshold is a specific voltage level you define to clearly differentiate genuine neural signals, such as action potentials or event-related potentials, from electrical noise or artifacts in your recorded data. This threshold acts as a gate, allowing only signals that surpass a certain strength to be considered for further analysis, ensuring you focus on the most relevant brain activity. The core reason we're relying on thresholds is to maintain the integrity of our data and the validity of our scientific conclusions. By setting a clear amplitude limit, we systematically exclude random fluctuations and low-level noise that could otherwise be misinterpreted as meaningful biological events. This prevents both false positives, where noise is mistaken for a signal, and false negatives, where true signals are too weak to be reliably detected without proper filtering and a well-defined cutoff. To practically set an effective amplitude threshold, start by thoroughly characterizing your baseline noise. Often, this involves calculating the standard deviation of your data during a quiet period where no specific neural events are expected. A common and robust practice is then to set your threshold at a multiple of this standard deviation, typically ranging from 3 to 5 times 4 detecting action potentials. For example, if your noise standard deviation is 10 microvolts, a threshold of 30 to 50 microvolts might be appropriate. Always visually inspect your raw data after applying a preliminary threshold to ensure you are capturing the signals of interest without excessive noise, and iterate on this process. Remember, different types of neural signals, such as spikes versus local field potentials, often requiring different thresholding strategies due to their distinct amplitude characteristics. For advanced applications, consider dynamic approaches like adaptive thresholding, where the threshold continuously adjusts based on changes in the background noise level. You might also explore robust statistical measures, such as the median absolute deviation instead of standard deviation, which are less sensitive to extreme outlier noise. Ultimately, a thoughtfully established amplitude threshold directly improves your signal-to-noise ratio, making your analysis more accurate and reliable, and paving the way for more confident interpretations of brain function. In essence, carefully setting an amplitude threshold is a fundamental step toward unlocking clear and reliable insights from complex neural recordings. It ensures that every neural event you identify and analyze is truly representative of brain activity, helping you build a solid foundation for your research and understanding.